Lanthanum-doped bismuth ferrite thin films have emerged as promising multiferroic materials due to their unique coexistence of ferroelectric and magnetic properties at room temperature, making them attractive for applications in data storage devices, sensors, and renewable energy systems. Pure BFO crystallizes in a distorted perovskite structure, R3C space group, and exhibits a high Curie temperature, 830 degrees Celsius, for ferroelectric order and Néel temperature, 370 degrees Celsius, for antiferromagnetic order. However, its practical implementation has been limited by several technical challenges, including the formation of undesirable secondary phases like bismuth iron oxide due to bismuth volatility during synthesis processes, as well as high electrical conductivity associated with point defects in the crystal lattice and the presence of mixed iron oxidation states. These issues generate high leakage currents that impair ferroelectric performance and hinder electrical polarization in real devices. To overcome these limitations, an effective strategy has been rare earth doping, particularly with lanthanum, which substitutes bismuth sites in the crystal structure. The similar ionic radio between lanthanum and bismuth enables efficient substitution without introducing significant lattice strain. Lanthanum doping has multiple beneficial effects. First, it stabilizes the perovskite phase by suppressing secondary impurity formation. Second, it reduces charge carrier concentration by decreasing oxygen vacancies and bismuth-related defects. And third, it modulates magnetic properties by inducing lattice distortion that affects BFO's antiferromagnetic ordering. Studies have shown that compositions with 10% doping exhibit significant improvement in spontaneous polarization, along with reduced dielectric losses. The sol-gel method, followed by spin coating deposition, is widely used for fabricating these thin films due to its low cost, excellent stoichiometric control, and ability to produce homogeneous nanoscale coatings. The process begins with preparing a precursor solution typically containing bismuth nitrate pentahydrate, iron nitrate nonahydrate, and lanthanum acetate monohydrate as metal cation sources. These precursors are dissolved in a solvent mixture that may include glacial acetic acid and ethylene glycol, which act as stabilizers to prevent premature metal ion precipitation. To enhance sol stability, chelating agent acetylacetone is added, forming complexes with metal ions and retarding hydrolysis. The resulting solution undergoes continuous magnetic stirring for 24 hours at room temperature to ensure homogeneous mixing. Film deposition is performed via spin coating, a technique allowing precise control over film thickness through substrate rotation speed. Before deposition, substrates are rigorously cleaned via ultrasound in acetone, ethanol, and deionized water to remove organic contaminants and improve wettability. The sol is deposited onto the static substrate using a micropipette, then accelerated to 4,000 revolutions per minute for 30 seconds to achieve uniform thickness. Immediately after deposition, films undergo thermal treatment, pre-annealing, at 250 degrees Celsius on a muffle Felisa, to evaporate residual solvents and decompose organic nitrates, followed by final annealing at 550 degrees Celsius for 1 hour in a tube furnace with oxygen flow system to crystallize the perovskite phase. This step is critical, as insufficient temperatures may leave the film amorphous, while excessive temperatures can promote bismuth volatilization and impurity formation. X-ray diffraction analysis of dopant BFO samples was performed using a Rigaku Ultima 4 diffractometer. The results revealed a pure rhombohedral phase, space group R3C, without secondary phases or substrate interference, as confirmed by comparison with reference. Rietveld refinement in full prof and microstructure analysis in MAUD provided reliable structural parameters. Notably, lanthanum doping induced anisotropic lattice distortions. The A and B axes expanded, while the C axis contracted. Additionally, the crystallite size increased progressively with lanthanum concentration. These changes were attributed to the smaller effective ionic radio of lanthanum in 12 coordination sites, modifying the unit cell volume. The study successfully correlated doping-induced structural changes with lattice parameter evolution. Surface analysis of BFO films was performed using optical microscopy, SEM, profilometry, and AFM, complemented by EDS spectroscopy, revealing nanoscale grains in pure BFO that coalesce into larger grains with doping. Notably, porosity decreased with higher lanthanum content, aligning with studies linking grain growth to dopant concentration. EDS confirmed compositional changes, supporting the observed microstructural evolution. AFM analysis revealed key microstructural changes in BFO films with lanthanum doping. The 2D and 3D topographies showed an initial roughness increase at 2% lanthanum, followed by a significant reduction at 4 and 6% lanthanum, attributed to crystallite refinement. Ferroelectric domain sizes exhibited complex behavior. Smaller domains at 2% lanthanum, structural disorder, stability at 2 and 4%, and abrupt growth at 6% lanthanum, suggesting dopant-driven reorganization. These modifications in roughness and domain structure directly influence the film's ferroelectric and electronic properties for device applications. Raman spectroscopy confirmed phase purity in lanthanum-doped BFO while revealing dopant-driven structural changes. Peak shifts and intensity variations indicated lattice modifications, particularly in bismuth and oxygen bonds. At 6% of lanthanum, peak broadening signaled increased structural disorder. Full width at half-maximum analysis quantified these distortions, linked to improved material stability and reduced impurities. These modifications are critical for enhancing BFO's optoelectronic performance in thin-film devices. FTIR analysis confirmed the purity and quality of the BFO thin films, showing no detectable organic residues like carboxyl, carbonyl, or hydroxyl groups that could compromise performance. The spectra revealed characteristic iron and oxygen bonds and bismuth and oxygen bond vibrations, confirming the expected inorganic structure. The absence of organic contaminants is critical to preserve optimal optical and electrical properties in devices. These results demonstrate the film's chemical stability and suitability for optoelectronic applications. The controlled synthesis ensures impurity-free material for use in solar cells or sensors. This work explored strategies to enhance the ferroelectric behavior of BFO thin films through doping. Electrical measurements using graphite contacts revealed characteristic ferroelectric hysteresis loops, confirming the material's functional properties. While most doped films exhibited promising ferroelectric performance, the 2% doped sample showed significantly degraded behavior compared to others. The results demonstrated that low doping concentrations can negatively impact ferroelectricity, whereas higher doping levels maintained or slightly improved the response. These findings provide crucial insights into how dopant concentration influences BFO's ferroelectric performance for potential device applications. Ferroelectric domain patterning of bismuth ferrite thin films was successfully demonstrated using AFM-based nanolithography. The technique enabled nanoscale visualization and control of ferroelectric domains through applied voltages, revealing stable polarization alignment after field removal, a critical feature for non-volatile memory applications. Contrast-enhanced images confirmed the persistence of reoriented domains, validating the material's potential for FIRAM devices and sensors. While measurement parameters like voltage, frequency, and scan area required sample-specific optimization, all tested films exhibited rewritable domain configurations. These results establish AFM lithography as an effective tool for both characterizing and engineering BFO's ferroelectric properties at the nanoscale for advanced electronics. The study revealed light-sensitive diode-like behavior in lanthanum-doped BFO films, with polarization states altering current voltage responses. While zero-bias photocurrent confirmed photovoltaic potential, performance was limited by defect-driven leakage currents that disrupted stable polarization. These findings highlight both the promise for photodetectors and the need to minimize defects for solar cell applications. In conclusion, homogeneous lanthanum-doped BFO thin films were successfully synthesized via spin coating and calcination, exhibiting optimal rhombohedral R3C structure with controlled thickness between 60 and 200 nanometers and minimal organic residues. Characterization confirmed ferroelectric/piezoelectric behavior via PFM and AFM lithography. though domain stability was affected by defects. The films demonstrated photovoltaic activity with zero bias photocurrent and reduced band gap under lanthanum doping, highlighting their optoelectronic potential. However, leakage currents from oxygen vacancies limited remanent polarization switching, underscoring the need for improved defect management. These results position lanthanum-doped BFO as a promising multiferroic material for photovoltaics and memory devices, pending structural optimization to mitigate leakage pathways.